So what we have here is a very simple pulley problem, which I'll use as a first step towards solving more complicated pulley problems. In this one, I have two blocks that are connected to each other by a string that's draped over a pulley. I'm given the masses of the two blocks, m1 and m2. Gravitational acceleration is always given, and I want to find the acceleration of block number 1 here. Now I'm going to make what I call the usual pulley assumptions. So the pulley is effectively massless and frictionless. The string itself will neglect the mass of that thing, and we'll say the string does not stretch. And that would allow us to make some nice little statements about tensions in the string. We'll get to that in a moment. But one thing which I should note right up front is that although I'm given mass 1 and mass 2 here, when I solve the problem, I do not know which one is bigger. I don't know whether mass 1 is heavier than mass 2 or vice versa. So I don't know up front whether block number 1 here accelerates upward or downward. So whether it goes up or down should pop out of the solution. It should become evident in the mathematics. So to begin, let's start with the usual place. Let's draw some free body diagrams. So the free body diagram for block number 1 should look like the following. Block number 1 has some weight pulling on it, or gravity pulling on it. So we got m1g in the minus j hat direction, j hat positive upwards. And I'll have a tension in the rope pulling upwards. So I'll call that T in the j hat direction. Moving on to free body diagram number 2, again we have a tension pulling upward, and I'm going to call that T in the j hat direction. We've got a weight pulling downward, so minus m2g in the j hat direction. These two weights differ, right? m1, m2, different weights in general, but I've written the tensions to be the same. You might wonder why they're the same. You might have heard some rule of thumb at some point, maybe in a statics class, maybe it's someplace else, or physics class, perhaps. You may have heard the tension is constant along that rope, and the reason why it's true comes from our pulley assumptions. It's not something that's generally true in overall, but if we have a frictionless, massless pulley and a massless string here, that's where it comes from, and I have another video that'll show why that's true. But when we have these pulley assumptions, we can say that these two tensions are the same, and we will in this problem. Now the next thing I'm going to do is start drawing mass acceleration diagram. Now the way I'm going to do it might rub some people the wrong way, so just bear with me for a second. So here's m1a1 in the j hat direction, so I'm going to draw the mass times acceleration upward here, and I'm going to do the exact same thing with block number 2 here. So I'll call this m2a2 in the j hat direction. Now I know these both can't possibly be right. If one's accelerating upward, then the other one might be accelerating downward. At least maybe I know in my gut that they can't be right. But these accelerations are unknown to me. So whenever I have an unknown acceleration, I like to draw it in the positive j hat direction. And then I'll let the mathematics tell me the signs of these things. In fact, maybe I'll put down here just as a little note, I'll say to myself that I expect that A1 and A2 will have opposite signs. In other words, if one's accelerating upward, the other one will be accelerating downward. Now let's think about where we're going again. This is a relatively simple problem in that we're only looking for an acceleration. We don't have to find out a displacement or velocity or anything like that. So all we have to do is apply F equals ma, and boom, we've got our acceleration, and we're done. That's kind of nice, or at least kind of convenient for us in this case. So again, what I have here is a whole bunch of forces. I've got some mathematical expressions for acceleration. The way I get the acceleration is to apply Newton's second law, F equals ma, and I'm off to the races. So for block number 1, well, everything's going on in the j hat direction. So block number 1, j hat direction. What am I going to get? Let's just read it right off. I get the tension upward minus the weight of block 1 down is equal to mass of block 1 times acceleration of block number 1. So there's my first equation. Give it a number, equation number 1. So for block number 2, again, I look in the j hat direction. I've got the tension pulling upward. In fact, it's the same tension minus the weight, m2g is equal to, this was m1a1. Now we have m2a2 A2. Again, since I've drawn this positive, I've got no negative signs in here at all. And that's what I will call equation number 2. Now I want to observe something. We've got a set of equations here. I've sort of exhausted all my physical principles that I can apply, giving me 2 equations. How many unknowns do I have? Well, let's think about this for a second. I don't know the tension, right? So there's an unknown. I don't know the acceleration of block number 1. In fact, that's what I want to find. And I don't know the acceleration of block 2 either. So it looks as though I have 3 of these things. And this is disturbing because I got 3 unknowns and only 2 equations. My equations, or my system, seems underdetermined in some sense. So what I need to do is to somehow find another equation here, another physical principle, or maybe other principle that relates 2 or more of these unknowns. And the answer comes from kinematics. Kinematics is sort of mathematical relationships to motion that come only from definitions of what motion means, or what constraints are on the system, and not directly from physical equations themselves. So for example, let's think about my pulley system here. Let's suppose block number 1 went up 1 foot. What would happen to block number 2? Well, block number 2 would go down 1 foot. Maybe I should put these in centimeters or something like that. So let's say block number 1 goes up 20 centimeters. Block number 2 is going to go down 20 centimeters. Let's say block number 1 goes down 30 centimeters. What happens? Block number 2 is going to go up 30 centimeters. There's a one-to-one relationship between the motions of these 2 blocks, aren't there? And that's because of the constraint. We said that we have this cord, or a rope, connecting those 2 things, and that rope does not stretch. That's part of my pulley assumptions. So if one block moves one way, the other block must move the opposite way, but by the same exact amount. There's that one-to-one relationship between those. That does not come from F equals ma, it just comes from the constraint. So let's suppose block number 1 moves up that 10 centimeters in 1 second. So block number 1 would be going 10 centimeters per second, at least on average. Then block 2 must be going down at 10 centimeters per second, right? The exact same speed, opposite direction. Now let's say block number 1 is going up and its speed is changing, its velocity is changing. Maybe its speed is increasing at the rate of 32 centimeters per second squared. Well, then block 2 would be going in the exact opposite direction, or accelerating in the exact opposite direction at the same rate, right? If I got 32 centimeters per second squared up, then I have 32 centimeters per second squared down for block number 2. So you see there's a one-to-one relationship between these motions. It comes from kinematics. So I'll just say kinematics tells us that A1 is equal to minus A2. Again, same magnitude, just opposite direction, hence the minus sign there. I've got a third mathematical relationship relating my 3 equations. And you can, if you're a mathematician, you might want to check whether these relationships are indeed independent relationships. But they are, I guarantee it, in this case. So now I think I'm ready to solve. So I got my 3 equations, 3 unknowns. Let's just rewrite this first equation. So here's our equation 1, just repeat it again. Scroll down a little bit. Now what I'm going to do is take equation number 3 and substitute it into equation number 2 here. So when I do that, I'll get T minus M2G is equal to minus M2A1, right? 2A1. So A2 is equal to minus A1, so I just make that substitution right here. So now look what I did. I've got 2 equations now with 2 unknowns. My 2 unknowns are T and A1. I've eliminated the A2. So I should be able to take these 2 equations and solve for the A1. Before I do that, I want to point one thing out. Remember when I said that we would take as my mass acceleration diagrams both accelerations pointing upward? At least that's sort of the default. So positive A1 would mean this thing is accelerating, block number 1 is accelerating upward. A positive A2 would mean that block number 2 is accelerating upward. But our kinematic relationship says, oh, these have to be in opposite directions. So A1, if A1 is accelerating up, A2 has to be accelerating downward. So I've sort of encapsulated or captured that thing that we knew from the beginning in this kinematic relationship right here. So because I put that minus sign there, now my equations are completely consistent with the physics of the problem and everything we know about the system. When one block goes up, the other block has to be going down or accelerating down. So I've got a well-formed system of equations here, and I don't have to do any sort of backtracking in terms of trying to keep track of signs, because everything's defined consistently. Now getting back to my equations here, as I said, I had two equations, two unknowns to t and the a1. I can solve these equations simultaneously. I can do some sort of substitution or elimination of the unwanted variable, the t, and I'd be able to solve for the acceleration that I'm interested in. So rather than bore you with those details, they're pretty straightforward manipulations. In the end, what you get is a1 is equal to m2 minus m1, all times gravitational acceleration, divided by m2 plus m1. Stick with it. And this is an interesting result because it's rather profound. So let me put a box around it first. Actually, let me check the units, and then I'll tell you why it's interesting. So I got an acceleration here. So let's do the unit check. Units. Acceleration here. Acceleration is a length over time squared. And on the right-hand side, what do I have? This equals, hopefully, mass 2 minus mass 1, that's a mass, divided by mass 2 plus mass 1, that's another mass. I can just say mass plus mass over mass plus mass. And then I multiply this whole thing by a g, which is a length over time squared. So mass plus mass is a mass, mass plus mass is a mass, mass divided by mass is 1, and I just get a length over time squared, right? Length over time squared checks. So units are cool. But let's check that this makes sense. So what's the sign of A1 going to be? Is it going to be positive or negative? Well, it depends upon the masses, and that's what we expected, right? If we have this pulley system right here, and if one of these masses was bigger than the other, let's say mass 2 is bigger than mass 1, what's going to happen? You release it, let's say, mass 1 is going to start heading upward, right? It's going to start accelerating upward. Again, if mass 2 is bigger than mass 1, I expect A1 to be positive. Well, let's look at my little result over here. If mass 2 is bigger than mass 1, then this difference here is going to be positive. G is a positive number. Denominator is positive. So, again, if mass 2 is bigger than mass 1, A1 is positive, exactly as I expected. Again, and if I flip it, if mass 1 is bigger than mass 2, then acceleration 1 should be heading downward, right? So again, if mass 1 is bigger than mass 2, then this numerator is negative divided by something positive times something positive. So acceleration will be negative. So I got these. So again, this is what I meant earlier, that the direction of A1 will pop out of the mathematics, right? So here's the relationship that tells us which way we accelerate. If M2 is bigger than M1, we accelerate up, and then vice versa. So that's really nice how that's embedded in there. And there's my answer.